Hello everybody, and welcome to another lecture on computer architecture. Today I want to talk to you about the instruction set of MIPS. And as you know, MIPS is a reduced instruction set computer. So it will not take me much time because we only have a few instructions available to us. So let's get started. You will see the entire set of instructions. Once again, here on the left, you will see the architecture. If you don't understand this kind of things, then go back to that lecture where I described this. But in brief, we have here 32 registers that can be serving as input, for instance, source, target, and a destination. This is the names that I will use. They can be processed in the arithmetic logic unit and then be placed in the registers and to do more operations. Also, they can be placed in main memory, so that's outside the main processor normally. But sometimes they can also be, when you have cache, they can also be inside. But for the moment, let's just say that this is outside the processor. Then we have the instruction register, where the instruction to be executed is residing. And we have the program counter that counts to the next instruction in main memory. So this is the architecture we're going to use. And the instruction set, as we know, is a reduced instruction set, meaning we have just a few instructions available. And these instructions, as we know, are here. The type of instruction we're going to do is here saved in the opcode, in the instruction register. And it has 6 bits, so you have 2 to the power 6, which is 64 different instructions possible. So that's quite limited. And we can easily describe them here in a single lecture. So let's take a look here. But first I want to remind you that all instructions are actually of the type 2 operands in and 1 operand out. So all of them basically, well, not always, but basically it is like this. You have 2 input operands that you have to specify, and you have to say where you want to store the information. So everything has basically a source operand, a target operand, and a destination operand. So let's take a look. The first one here is the set of instructions here. Maybe I will put it a little bit on the left to not put my face in front of it. The first set of instructions is what we call the logic and the shifting functions in general. These shifting functions here, there are 6 of them. For instance, SLL, which means shift left logical. Shift left logical, it takes an operand. In this case, the target operand. Well, I will show you in a moment why this is going wrong. I will, because when I wrote this and when I prepared this to think about what I was going to say, I see that something is wrong here. Because it takes the target operand, okay, so that can be, for instance, one of those of the 32 registers, can be the target operand, and then it will shift a number of bits to the left, this operand, and then store it in the destination. That's okay. But this num, the number of bits we want to shift to the left, is part of the instruction itself, so what we call immediate. To show you this, the part of immediate, the format of this type of instructions, remember, was the opcode, 6-bit, then specifying 3 operands, each 5-bit, then here a number, which we call immediate, and then the subfunction we're going to use, if possible, if needed. So this num is part of the instruction itself. So that comes from here, this immediate value. So now we have a problem because this immediate also goes to the target register here. So this, of course, cannot be true that we have this one going to the target and this one going to the target register. So this one, my excuses, this one should have been called the source register. So what do we get? We take the source register, shift it a number of bits specified in the instruction itself, and then this operation is performed by the arithmetic logic unit, and then the answer is stored in the destination register. So we can do this left shift, we can do it right shift, we can do it shift right arithmetic. I will not tell you the difference between the two, but that will be clear in the end of this lecture series. I will go back to this shifting things. There also can be have that the number of bits is specified not by the function itself, not by the operation itself, but actually is stored in one of the registers. So maybe T0 stores that we want to shift left 5 bits, then this information actually is then contained here in this register. And we use shift left logic variable. Okay, then the next set of instructions is the arithmetic functions. So we have add, subtract, add immediate unsigned, sub unsigned, subtract unsigned. We have multiply, we have division, and of course this is all integer. Don't forget, these are all integer calculations, various sorts. Note that if you multiply two 32-bit numbers, then the result can be 64-bit wide. Also with divisions, if you do divisions, then you can have the division itself and you can have the remainder, as you know. So these two things actually, that's why they're a little bit special, because if you multiply, actually the result does not go directly to the destination register because they're only 32-bit, but they go to an immediate register, which I didn't show here. But they are, I think I'm sitting in front of it, they are going to the high and low register. And then from there you can do something with this register. For instance, you can push them into one of the other registers. It will be clear because the next lecture I will talk about arithmetic. Then we have here the logic functions, and immediate, or, nor, or immediate, exclusive or, and exclusive or immediate. Remember the difference between, for instance, and immediate is that one of the with immediate, one of the operands is inside the instruction register, so inside the instruction itself. But for the rest, I think these things are quite logical. This is what we call bitwise operations. Here we have logic, direct logic operations. So for instance, we have here the source and the target register. The source and the target register. If what is it? If the target register is smaller than the source register, then place a 1 in the destination register. So we're comparing here these two registers here that are entering here, these two values, and then if one is smaller than the other, then we're placing a 1 in the destination register. If not, we place there a 0. This comes in handy when we're doing branching and comparisons in general. As we will see, these ones will implement some of the branching functions. So also here we have with immediate, we have unsigned, we have the non-immediate versions. That I think is also then clear. So this is how the right side page then is saying how this is then the format of the instruction itself, the complete format, which we not discuss here today, but which we did already in last lectures. So let's go to the next set of instructions, which is jumping. So we have here, for instance, jump address. It directly just what it is doing, it is putting the address that is part of the instruction. Let's see, let me put here back, the format was J, the format is J, and in J you have here the opcode, which is jump 6-bit, and the other 26-bit, then specify the address where to jump to. And what it is doing, it is simply placing this address then into the program counter, so that next time in main memory the next instruction will be the one placed in the instruction register, will be the one pointed to by this address. Jump and link, this is the same, but then also the current program counter is saved in one of these registers. We will see this when we do functions. Jump on register, meaning what it is doing, it is taking one of these registers and placing it into the program counter. So it goes here, for instance, if you take T0, it goes through the arithmetic logic unit, and then this address is placed in the program counter. Jump on link and register is also, well, these things will become more clear when we talk about functions. The next one is branching. There will also be a complete lecture on branching itself, how we're going to implement the if function that we know from C programming. I'm going to show this on the hand of these branching instructions. But I want to point out that of these, 6 branching instructions, actually only 2 of them, these first 2, are implemented in hardware. The other ones are pseudocode. As I can show you, this is the right page then. Branch on equal, this is one where you have, is of the immediate type. And the others that you have in branch on not equal also, these are real instructions implemented in hardware. And the others that you have here, 4 of them, they are format is P, meaning they are pseudo instructions, meaning that the compiler will translate them in other instructions, as we will see, or as we have already seen actually with the hello world example, that the load address, for instance, was pseudocode, and it was split into 2 real hardware instructions. Okay, continuing. So these are the branching, meaning that the program counter will be changed only if a condition is met. If not, then it just continues business as usual, meaning actually it will just add 4 to the program counter. Program counter is loaded, 4 is added to it and put in the program counter so that it points to the next instruction in memory. Okay, next we have move from high, move to high, move from low and move to low. Okay, move is actually just copying one register and putting it into the other. And I want to point out also here that move, I have to go to the right side page, move is also pseudocode. It doesn't exist. The move instruction, meaning actually it is copying, it's not moving, it's copying. It would be copying one register and placing it into the other. It doesn't exist. How it is implemented by the compiler, it is actually taking one register as a target and then adding the 0 register to it, which is always 0. So then this one contains the source here, this one contains the original register, and then added 0 to it, and then placed in the destination register. So it's a pseudocode, but for the moment it doesn't matter. The other ones are, I told you, the arithmetic. The answers are placed in the high and the low registers, and from there you can move from high, or actually you can also place something in this register if you want. So these are these move instructions. Next set of instructions is the loading and storing, and these pertain to the external memory. So you can load from memory, load a word, and then place it into one of the registers. So for instance here read, it can go here, destination. So you can for instance where is it, load word. It is then taking one of the memory addresses and fetching the word 32-bit that are there and placing it into the register. You can also put half a word, so 16-bit, and you can also load a byte which is just 8-bit, as you know. Same for storing, store byte, store half word and store word. You can actually do it with offset, meaning that the address that you specify, another register is added to it, and then the final address then is, the contents of that final address then is fetched and put in the destination register. This comes in handy when you have arrays. You just have a base address and then you do offset this with then your index that you have calculated in your array. Continuing, I think it still has, no, this has already all the load and store instructions that go to here to main memory. Finally, let's see, I think we already finished actually, because the last instructions, these instructions here, they are floating point, and I will leave it for the other lecture when we're going to talk about floating point, but you can already see here it also has load, single word, load word, floating point load, floating point store. It has also here this kind of comparison of two floats, and it has add, sub, multiply and division, but none of course with floating point, which is a little bit more complicated. Finally, something very important is this software interrupt is a system call. And I didn't talk about interrupts yet, but what this is doing, when you place a system call, it hands over execution to the operating system. For instance, when you want to print something on the screen, or when you want to get generate maybe random numbers, or maybe you want to get input from the user, this is handled by the operating system, by the kernel. And we can get access to these functions which are we are not going to write. For instance, print float, for instance. We're not going to write these instructions. We just place a system call. And with the system call, we have to supply the necessary, the relevant information. We have to place it in certain registers. I will talk about it in the next lecture, actually, about system calls. We have to place the relevant information in registers and then do the system call. So this ends the entire, this summarizes the entire set of instructions we have available to MIPS. As you can see, it's quite few. We have just some shift instructions, some arithmetic instructions, some bitwise logic instructions, some comparison instructions, some jump instructions, some branching instructions, some moving instructions, because that is to say copying instructions from one register to another, and copying, loading and storing instructions to main memory. And finally we have the all-important system call, because a computer that doesn't generate output is not a computer, but it's just a stupid machine. Okay, see you in the next lecture.